That giant television hanging on the wall of your living room may not be the future of entertainment after all. For more than 100 years, we have accepted the same basic idea. If we want to see something digital, we need a surface to display it on. First came film, then bulky televisions, then plasma, LCD, OLED, and incredibly thin 4K and 8K panels. The image kept getting sharper, the colors kept getting brighter, the screens kept getting thinner, but the fundamental idea never changed. You were still looking at light coming from a flat surface. Now, researchers in China are working on a radically different approach. Instead of putting an image behind glass, the goal is to create the image directly inside physical space. Not on a television, not inside a phone, not through a headset, but floating in the air around you. Imagine walking into your living room and seeing a glowing three-dimensional object suspended several feet in front of you. You walk to the left, and you see its side. You walk behind it, and you see the back. Move closer, and the perspective changes naturally. There's no black rectangle on the wall, there's no piece of glass between you and the image, and there is no headset covering your eyes. This is the promise of volumetric display technology. And if engineers can take the technology from laboratory experiments to affordable consumer devices, it could completely change the way humans interact with digital information. Because the biggest breakthrough may not be creating a better television, it may be discovering that we never needed the television screen in the first place. To understand why this technology is so important, we need to start with one deceptively simple question. How do you make light appear in a place where there is nothing for that light to hit? That sounds like a problem from science fiction. But it is exactly the problem researchers have been trying to solve. Think about shining a flashlight through a completely clean room. You can see the light when it reaches a wall. You can see it when it hits dust or smoke. But the beam itself does not normally become a solid object floating in the middle of the room. Light travels through space. It needs something to interact with before your eyes can perceive a bright point. That is why traditional displays need a surface. A television sends light toward your eyes from millions of tiny locations across a panel. Those locations are pixels. Each pixel can change its brightness and color. Together, millions of pixels create the illusion of a moving scene. But there is a fundamental limitation. Every pixel exists on the same flat plane. No matter how advanced the television becomes, the display is still fundamentally two-dimensional. A volumetric display tries to change that. Instead of arranging pixels across a surface, it attempts to create tiny points of light at different positions throughout three-dimensional space. These points are often described as voxels. Think of a voxel as the three-dimensional equivalent of a pixel. A pixel tells you where light should appear on a screen. A voxel tells you where light should appear inside a volume. And that difference changes everything. Imagine trying to draw a glowing human face using thousands of microscopic points suspended in the air. One point would not look like much. It would simply be a tiny spark. But if you could control thousands or millions of those points with incredible speed and precision, you could create the appearance of a complete three-dimensional object. The challenge is controlling those points. Researchers have explored several methods for achieving this effect. One approach involves manipulating microscopic particles with highly focused laser beams. The particle can be held in a specific location using optical forces. Once it is positioned, additional light can make it glow. The result is an incredibly tiny luminous point existing somewhere in three-dimensional space. Now imagine moving that point extremely quickly. Instead of allowing it to remain in one position, the system rapidly changes its location. It can trace a path through space. Your eyes cannot individually follow every position when the movement becomes fast enough. Instead, your visual system combines the rapidly changing points into what appears to be a continuous shape. It is similar to what happens when someone spins a sparkler in the dark. A sparkler is actually just a bright point moving through space, but when it moves rapidly enough, you see what appears to be a glowing circle or pattern. The technology takes that basic visual principle and pushes it into an entirely different level of precision. The difference is that a laboratory system can control the location, brightness, and color of microscopic points with carefully coordinated optical systems. Instead of drawing a circle with a sparkler, it can potentially trace the outline of a complex object. A vehicle, a face, a mechanical component, a geometric structure, or eventually much more complicated scenes. And this is where the idea becomes genuinely fascinating. The screen disappears. The room becomes the display. You're no longer looking at a digital world through a rectangle. The digital object is placed directly into the physical environment. But there's another approach that makes the concept even more futuristic. Instead of relying on a physical particle, researchers have also experimented with extremely concentrated laser energy interacting with the air itself. Under the right conditions, intense laser pulses can create tiny luminous plasma points. Those points can appear as flashes of light in open space. Move the point rapidly enough, and the same persistence of vision principle can produce recognizable shapes. It sounds like science fiction. But the underlying idea is surprisingly straightforward. Create a point of light, control where it appears, control how long it exists, move it rapidly, repeat. The difficulty is not understanding the concept. The difficulty is engineering a machine capable of doing all of it with extreme precision, safety, speed, and efficiency. That is where the real challenge begins. Because creating one floating point is one thing. Creating a convincing three-dimensional image is something else entirely. The system has to calculate where each luminous point should appear. It has to control the optical equipment accurately. It has to synchronize the movement with the desired image. And it has to repeat the process fast enough that your eyes perceive a stable object rather than a collection of individual flashes. Every tiny error matters. If the timing is wrong, the shape can distort. If the position is inaccurate, the image becomes unstable. If the brightness is inconsistent, parts of the object disappear. And if the system cannot operate efficiently, it becomes far too expensive and complicated for ordinary consumers. This is why laboratory success does not automatically mean that holographic televisions are about to appear in stores tomorrow. There's a massive difference between proving that something is physically possible and turning it into a practical consumer product. But that distinction does not make the breakthrough less important. In fact, it makes the current moment more interesting, because the basic question is no longer simply whether three-dimensional light can be manipulated. The question is how far engineers can push it, and that creates a fascinating comparison with the direction taken by some of the world's largest technology companies. For years, the major technology industry has been trying to escape the limitations of the traditional screen. But instead of removing the screen, one popular solution has been to bring it closer to your eyes. Virtual reality headsets are a perfect example. Inside a VR headset are incredibly sophisticated displays. Sensors track your head. The viewer would become part of the visual experience. Now take that same concept outside entertainment and imagine an engineer designing a new vehicle. Today, the design can be viewed on a monitor, converted into a 3D model, or explored through virtual reality. But imagine the complete vehicle appearing physically in the center of a conference room. The engineering team could stand around it, examine proportions, discuss components, compare different versions, and interact with the digital model as if it occupied the same physical space as the people discussing it. Now imagine medicine. A doctor studying a complex anatomical structure could potentially examine a three-dimensional representation rather than relying entirely on flat images. Instead of mentally reconstructing depth from multiple scans, the physician could examine a spatial model from different angles. Again, the screen would no longer be the center of the experience. The object itself would become the interface. And this idea extends far beyond television because architecture, education, engineering, scientific visualization, communication, and even the basic design of a home could change. For decades, our furniture has been arranged around screens. The television sits against a wall, the couch faces it, chairs point toward it, and the entire room is organized around a flat rectangle. But what happens when the rectangle disappears? The center of the room could become the display, and a small device on a table could generate the visual experience without permanently occupying an entire wall. When the display is turned off, there is no giant black screen dominating the room. The room returns to being a room. That sounds like a small lifestyle improvement, but at industrial scale, it could represent a huge economic shift. Consider how many industries depend on displays. Smartphones need displays, laptops need displays, tablets need displays, televisions need displays, automotive dashboards need displays, and control rooms depend on them as well. Industrial machines use displays, airplanes use displays, medical equipment uses displays. Billions of people interact with flat screens every day, creating a huge global supply chain built around manufacturing them. Factories produce panels, companies develop display materials, manufacturers build specialized equipment, suppliers produce components, and software designers create interfaces specifically for rectangular screens. Entire industries have grown around the assumption that digital information must be displayed on a surface. If that assumption changes, the consequences could spread far beyond entertainment. But there is an important reality check. A new display technology does not automatically destroy the old one, because history shows that technologies often coexist for decades. The automobile did not instantly eliminate the horse. Digital cameras did not immediately eliminate film. Smartphones did not instantly eliminate personal computers. And a volumetric display will not suddenly make every television disappear. Before that could happen, the technology would need to overcome enormous engineering challenges involving size, cost, power consumption, safety, resolution, brightness, viewing distance, color reproduction, reliability, and manufacturing. Perhaps the biggest challenge of all is this: how do you create a large, detailed image without turning the machine into a giant industrial system? A laboratory prototype can tolerate complexity. A consumer product cannot. A laboratory can use expensive optical components, but a television sold to millions of households cannot cost a fortune. A laboratory can occupy an entire room, while a consumer device needs to fit naturally into a practical living environment. This is where technological history becomes important. Almost every major technology begins in a form that looks impractical. Early computers were enormous, occupied entire rooms, consumed huge amounts of power, and required specialized environments. Today, a device thousands of times more powerful can fit into your pocket. The earliest mobile phones were also huge compared with modern smartphones, expensive, limited by battery life, and restricted in usefulness. But engineers kept shrinking them. The same pattern appeared with televisions, cameras, processors, storage, and countless other technologies throughout history. The first version does not need to be perfect. It only needs to prove that the fundamental idea can work. Once the physics are demonstrated, engineers can spend years improving everything around it. Smaller components, better control systems, more efficient lasers, faster processors, improved cooling, higher precision, and lower manufacturing costs can gradually transform an impossible-looking machine into something practical. That is why the current stage of volumetric display research deserves attention. The technology does not need to replace your television today. It only needs to continue improving. Because once a completely new display architecture becomes practical, the possible applications could grow rapidly. Imagine a future smartphone that is no longer primarily a screen. Perhaps it becomes a compact computing device that creates a temporary visual space when needed. You could place it on a table, activate it, and instead of staring down at a rectangle, interact with information floating above the surface. A video call could become more spatial, a map could become three-dimensional, a product preview could appear at realistic scale, while a teacher could display a rotating model of a molecule. A mechanic could inspect a digital engine, and a student could explore a three-dimensional historical structure. The interface would stop behaving like a web page and start behaving like a physical environment. That could fundamentally change how humans think about digital information. For generations, we have trained ourselves to understand screens. We swipe, scroll, click, zoom, and drag. These actions exist because we are interacting with a flat surface, but spatial computing does not necessarily have to follow those rules. If the object exists in 3 dimensions, perhaps the interface itself can become 3-dimensional. You could move around an object, look underneath it, examine its interior, and compare it with another object. You could interact with information based on physical position. The room itself becomes part of the computer, and that leads to perhaps the biggest implication of all. The boundary between digital and physical reality begins to disappear. Today, digital information lives inside devices. You open a phone to access it. You open a laptop, turn on a television, or put on a headset. The information remains trapped inside a piece of hardware. A volumetric display reverses that relationship. The computing system remains inside a device, but the visual result can appear outside the device. The machine becomes almost invisible, while the information becomes visible. That represents a completely different philosophy of technology, and it is one reason this field could eventually become much larger than holographic entertainment. But there is still one enormous question. Can these systems become safe and affordable enough for ordinary people? Controlling intense optical energy in open space is not something engineers can approach casually. A laboratory system has to be carefully designed. A consumer device would need strict safety standards and would have to prevent harmful exposure. It would also need to operate reliably around children, pets, furniture, and other objects. It would need to function for thousands of hours without constant maintenance. And it would need to become simple enough that an ordinary person could operate it without understanding the physics behind it. That is a huge challenge, but it is also exactly the kind of challenge engineering has solved repeatedly throughout history. The important point is that we should not confuse a promising prototype with a finished product. The technology is not going to magically replace every television tomorrow. There is still a long road between laboratory demonstrations and mass-market hardware. But that road becomes much more believable once the underlying physical principles have been demonstrated, and if engineers eventually solve the remaining problems, the transformation could be enormous. Think about your living room again. There's a television on the wall, a black rectangle waiting to be turned on whenever you want entertainment. When you are finished, you turn it off, but that entire model could eventually become unnecessary. Instead, imagine a small device sitting quietly on a shelf. You activate it, and a 3-dimensional scene appears in the center of the room. You walk around it, change the content, and interact with it. Then you shut it down, and the image disappears. Nothing remains. No giant screen, no permanent rectangle, just empty space. That is the real promise of volumetric displays. It is not simply about better pictures, higher resolution, or brighter colors. It is about the possibility of removing the physical boundary between the viewer and the image. For more than a century, technology has focused on improving the window. Sharper glass, thinner glass, brighter glass, more pixels, more colors, and higher refresh rates have all pushed traditional displays forward. But perhaps the next revolution is not another improvement to the window. Perhaps it is eliminating the window entirely. And if China or any other country manages to turn this concept into a reliable consumer technology, the consequences will extend far beyond televisions. The companies that dominate screens today would have to adapt. Software developers would have to rethink interfaces, while hardware manufacturers would have to redesign devices. Content creators would have to learn how to create for three-dimensional space. Consumers would also have to learn an entirely new way of interacting with digital information. The transition would not happen overnight. It would probably begin with specialized applications. Museums could use it. Research laboratories, medical facilities, engineering firms, military and industrial visualization systems, and entertainment venues could also become early users. Then, if the hardware becomes smaller and cheaper, it could gradually enter homes. Eventually, what looks impossible today could become ordinary. That is how technological revolutions usually happen. At first, the machine looks strange. Then it becomes expensive. Companies begin competing to improve it. The hardware gets smaller. Manufacturing scales, and prices eventually fall. And one day, people stop thinking of it as futuristic. They simply use it. The television followed that path. The smartphone followed that path. The computer followed that path as well. And someday, the same thing could happen to three-dimensional displays. The question is not whether the first prototypes look impressive. The bigger question is what happens if engineers keep improving them for another 10 years? What happens if the equipment becomes small enough to sit on a coffee table? What happens if the cost falls low enough for ordinary families? What happens if the images become bright, detailed, colorful, and stable enough to look completely natural? At that point, the question changes. We would no longer be asking whether holographic displays are possible. We would be asking why we ever accepted flat screens in the first place. Because the most disruptive technologies do not simply improve an existing product. They make the old assumption feel unnecessary. And that may be exactly what is happening here. For a century, we believed digital images needed a surface. Now researchers are challenging that assumption. They are experimenting with ways to create controlled points of light inside physical space. They are exploring how microscopic particles, lasers, plasma, optics, and extremely precise timing can turn empty air into a visual medium. There is still a tremendous amount of engineering left to do. But if those obstacles are eventually overcome, the result could be one of the biggest changes to human-computer interaction since the invention of the graphical display. The screen would no longer be something you look at. The screen would become the space around you. Your living room could become a cinema, your desk could become a laboratory, while your classroom could become a planetarium. Your conference room could become a design studio, and your phone could become almost invisible. The digital world would no longer be locked behind glass. It would exist around you. And perhaps the strangest part is that the first step toward that future is not creating more pixels. It is learning how to create a single point of light where there is nothing. Because once you can control one point, you can begin controlling thousands. Once you can control thousands, you can begin creating shapes. Once you can create shapes, you can begin creating objects. And once those objects can exist anywhere in three-dimensional space, the entire concept of a screen starts to look like an old idea. The television hanging on your wall may still have many years ahead of it, but the technology that eventually replaces it may not look like a better television at all. It may look like nothing, just empty air, until you turn it on, and suddenly the future is standing right in front of you.